We're going to be exploring the transformer, and specifically the beginning parts of the structure which make up a transformer. Before I do that, it's important to understand the concept of a token. Essentially, AI systems do not understand words, right? They're computers, and because they're computers, they don't understand actual text. They can only understand numbers. So what we do is we take all of our words and we run them through a process called tokenization, where you essentially take all of the text and you chunk it into these units, these subunits of text, which are called tokens. And so that's why a token is essentially a chunk of text. Okay. Now, these tokens are identifiable through a token ID, which is simply a number that's used to represent that piece of text. And we're going to see this through an example of tokenization, which you can do through this website. It's called Tick Tokenizer. All right. But essentially, the important thing to know about this token ID is that it's really just a number, right? It doesn't have any sort of numerical meaning by itself, right? And to kind of exemplify that, I use the example of this, okay, in red. Essentially, let's say Apple was token 34 and then Ing was token 35. This can be possible. And the reason why I gave this example is to show you that even unrelated pieces of text can have very close IDs, right? Because an ID is arbitrary. It doesn't really matter what that number is. It's simply used for retrieval purposes of like what specific text represents what ID, okay? All right, so now that we understand that, let's look at a tokenizer that is used within an LLM more specifically. And we're going to do that through this Tick Tokenizer website. So what I'll do is I'll say, hi, my name is Hemet. Now, I was really specific in using the name Hemet instead of something like John or Abby. And that was because Hemet is a pretty rare name. I don't know many Hemets, and the name Hemet, it does not come on the internet that much. And that means that if you look within our tokenizer, and each of these colors are like a new token, you'll notice that Hemet is broken into two different tokens. It doesn't have like a singular token which is associated to that word Hemet. And this is an important thing to understand because tokenizers that are used within AI systems are not word level tokenizers. This means that not every single word will have its own associated token ID. Because if we were to do that, the vocabulary would become so big that the AI simply would not work. It would just be unrealistic amounts of hardware which we would need, right? And then also, that would mean if you get some sort of novel word like Hemet, which doesn't really come up in the English language that much, you won't know how to tokenize it because there isn't any sort of token which can be associated with that specific word, right? And that specific text. So instead, what we do is something called sub-word tokenization. Essentially, we create tokens for full parts of words as well, but also partial parts of words. Okay, so if a word is frequently found and if you see it a lot of times, well, then it will get its own token. But if you don't see it that often, and it's not really shown that much, then it would just be made up of different parts of tokens. Okay, and so that's what we're doing here. We basically have hem and then it. Now these two tokens were frequently seen. Okay, so these two like sequences of text were seen a lot within the internet. That's why they have the token ID of 34006 and then 278, right? And then conveniently, when you add these two together, it makes up the word Hemet. Spaces are also counted within like the tokens. You see that like that little dot just represents that specific space. And if I didn't add that space, then it would have like its own sort of token, right? It's a different token ID. See, it's 276,382, right? So that's another cool thing. But basically, why I wanted to use this sort of website was to kind of show you that, your tokens do not necessarily have to be just words, right? It can be like parts of words, which are kind of like glued together to create a unique word that's not really seen that much, right? Now, for example, if I took Hemet, which is kind of unique, and instead I said John, you'll notice that John gets his own token, right? The same thing is true with like Emily, for example, right? Because these are like frequently seen names within the internet. Okay. Now, what happens is that the transformer inputs tokens. Okay, it doesn't input like this text. What it does is it tokenizes these texts through like these tokenization softwares, and then once you have these tokens like these, right, then you can actually go through the parts of the transformer. And the first part will be using a feed forward layer, which essentially just means that data passes through this neural network layer in just one direction. It can't go like back and forth, and it's like the most simplest piece of layer that you have within a neural network, right? And so what happens is each of these tokens goes through this layer. And when it goes into this layer, you will basically convert this token, like the token ID, into an associated vector embedding. Now let's think why we would do this. Like, what's the reason for converting like this token into a vector embedding? Well, it has to do with this portion here. All right, it has to do with this portion here. Well, if we think about it, a token ID doesn't have any sort of numerical meaning, right? So we can't really use it to, create predictions because there is no meaning behind that ID. It's an arbitrarily given ID. So what we need to do is we need to actually have some sort of structure which can hold semantic meaning. Because at the end of the day, the human language, right, which is what this transformer through the LLM is trying to replicate, it holds meaning. Like the words I'm speaking right now, they hold meaning, and they are chosen specifically because of how they are related to one another, right? So what we need to do is we need to map the semantic meaning and this relationship with specific words. And we do that through vector embeddings. So how a vector embedding works is that it's essentially a vector, okay? So vector embedding obviously is a vector. And a vector, simplest way to put it, is a list of numbers. And each of these numbers is a dimension, okay? So I'm just going to put this in the center. Now, each of these numbers is also called a feature. So it's a feature, a number, or a dimension. You can call it either way, it doesn't really matter. The reason why it's called a feature is because it represents a specific aspect of the word. Now, we don't really know what that is because, through training it updates and whatnot. But conceptually that these specific numbers within the vector represent some sort of thing that word has. So for example, you could have, just to keep things simple, you could have, let's say, a 3D vector. And in this 3D vector embedding, let's say you have a number for gender, right? So 0.5 means, let's say, male, and 1 means female. You could have one for royalty. Let's say this is like some sort of like king or queen sort of word. So let's say you have a number for that. And then let's say you have a word for status. So we'll put that for status, right? So that's sort of how this works, right? Like these numbers over here, they just represent specific aspects of that specific word that you're talking about. Okay? And really, what I'm trying to say with vector embeddings as a whole is that they are essentially a representation of the semantic relationships and meanings of that specific word. Okay, and the way that these numbers come to be is through training. So at first, what happens is that you have these numbers. Okay, so in this case, this 512 just means that there's 512 different numbers, right? So 512 dimensions. Modern day LLMs can go like really high; it's ridiculous. It can go to like 4,000 and whatever. But really, the same concepts apply to a 3D vector as a 1000D vector, right? Now, essentially, each of these numbers is a trainable parameter. Okay. Now, what a parameter is essentially a random number. At first, it's randomized, and then throughout training, what happens is that based off of the training data that we get, the LLM and specifically the neural network, this transformer, is able to update these numbers in a smart way. It's through back propagation. That's the process. And it's able to update these numbers smartly so that you're able to essentially make accurate predictions. And so these numbers are part of that trainable parameters. Okay? So at first, these embeddings, the numbers within these embeddings are completely arbitrary and randomized, right? Usually through some sort of like statistical model, but it is random. And then throughout the training of this data, right, of the training data and the neural network, you're able to basically update these numbers so that they actually are reflective of the semantic meaning of that specific token that they're associated with. Okay? So now you essentially have these vector embeddings, and you know what vector embeddings are. Then what happens with these vector embeddings? So that's what this is, right? That's what this illustration is. So this was our tokens. They were passed through this feed forward layer, simplest neural network layer, just passes data just straight. And within that, you're essentially finding the associated vector embedding. All right, you're finding the associated vector embedding. And once you find the associated vector embedding for that specific token, then you can basically have these embeddings. And the way that we actually know the features, like the numbers, is through training, right? Through training and updating these numbers from back propagation within neural network. And so back propagation is really a neural network concept and something you don't really need to know per se. Like you can just understand the fact that these numbers are essentially these knobs which are like adjusted here and there until they reach like a happy medium of providing like an accurate prediction for the training data set. But if you want to learn the more of the details of how that works, definitely search up neural network, backpropagation, and all of that fun stuff, right? Then what happens is once you have these vector embeddings, these embeddings by themselves aren't that useful, right? So what we do is we do something called position encoding, all right? And what this does is it essentially allows us to create relationships between these vector embeddings. And I'm going to get more into detail about what position encoding entails within my next video, right? But for this video, I think this was enough. There's a lot that we went through, so I'm just going to do a quick little summary so that we're all good. First off, you need to understand what tokenization is, all right? And tokenization basically just means taking your text and finding chunks of it based off of a given vocabulary, okay? Usually, you have a vocabulary of around 100,000. So you have 100,000 unique symbols, which are these token IDs, right? So that's another way you can actually understand them, right? These token IDs, you don't need to think of them necessarily as a number, but rather it's a unique symbol. So each of these numbers they're not really numbers, they're just symbols which represent that specific piece of text as a token. And these tokens are what the transformer understands. So we feed that through the transformer, and then those tokens are fed through this neural network layer, specifically a feed-forward neural network layer, where you essentially have this mapping of tokens and their associated vector embeddings. So it finds for one specific token what that vector embedding is. And that vector embedding has the semantic meaning of that specific word. And the way we were able to determine that semantic meaning was through like features, which are these numbers which represent different aspects of the word. And the way we know that this is a good number to put for this specific position is through training this neural network on data sets. And these parameters, essentially, these are trainable parameters, updating based off of this training. All right. And then after that, we do this process called position encoding, which makes these vectors embeddings more useful. And we're going to learn about that a little bit more in our next video series.